So coming to our next problem, that is based on cell balance momentum, in which we have given a cylinder of radius r1 that is kept in a die which have a radius r2. We can see here that it has a radius of r2 and cylinder have a radius of r1, and the angular space between die and wire is filled with a fluid. This region, the shaded region is filled with a fluid in both sides, and we have given also that our wire, basically this cylinder is moving with a velocity v, and our die is kept constant. This die is kept constant, and the length of our die is length L, and the thickness between the die and wire which fluid make is tau T. We basically take it T. And what is happening here that when our wire is moving with velocity v, therefore the fluid that is in between the die and wire is also moving with some velocity, and at the as die is rest, at that point our velocity will be zero due to the no slip boundary conditions. So in this problem, they say that neglecting all the end effects, start from the cell balance, develop differential equation that relate our horizontal velocity Vz with the our differential velocity Vz with our velocity profile. So we have to obtain a velocity profile equation and flux profile equation for this problem, and also we have to find the force that was act on wire to move the cylinder. And also in this question we have to find shear stress as well, and we have to write all the assumptions that we take before solving this question. So we can see that this is the radius r1 of cylinder, and this is the radius r2 of die, and this is the length of our die, and wire is moving with a velocity v. So start from here. We are taking a differential element as 1 minute. So we are taking a differential element that is have a length of L and which have a thickness of dr. As we can see that here, our cylinder, our wire is having a length L. Okay, our wire have length L and having thickness of and having radius of r. But as velocity is vary in r direction, so we take a differential element of dr in r direction. So before concluding to this, we first know how it is vary, how velocity is vary in which direction. So coming to that, first assumption is that we take v theta equal to 0. We take v theta equal to 0 as we have mentioned that our wire is moving in a one direction, the 1D flow. There is a 1D flow, laminar flow. There is a 1D laminar flow, which is taking place in a z direction. This one, which is moving in this one z direction, and this is the r direction, and there is a theta direction here. We're basically taking a cylindrical coordinate which have our origin here on the left side of the cylinder. So we have the v theta equal to 0 and Vr is equal to 0 as we have the 1D flow, so it is also have to 0, and Vz is not equal to 0 as given in a question. So as Vz is not 0, this may be vary. This will be vary in some directions. Let's say it is vary in r, theta and z directions. So as we know that when velocity is moving, when our cylinder is moving in z direction, we have a symmetry across theta. We have a symmetry across theta. Due to symmetry, there is a no variation of velocity of z direction in theta. Similarly, as this is an incompressible fluid and we neglect all the end effects, so there is a no velocity variation in z direction. So there is only variation take place in r direction, and we can clearly see that as when our wire is moving with velocity v, the fluid that is attached to that, the fluid that is attached to that wire is also moving with velocity v. due to no slip boundary conditions, and the fluid which is attached to our die is not moving as the die is on rest. So we can see that this one, we can see that this was moving with a velocity b, and here the fluid is moving with velocity 0. It means that there is a variation of velocity in this direction, in this direction. Okay, so this direction velocity is vary, and this direction we take is as z direction. So our velocity is a function of, no, sorry, this is the direction of r direction. This is a basically r direction. So this is a function of r direction. Velocity is a function of r direction. Okay. As since we have velocity only in z direction, therefore we have basically we have the 9 flux conditions, 9 flux. We have a 9 equation for the flux. First one is that phi r r, and the phi theta r, phi z r, phi r theta, phi z theta, phi theta theta, phi z z, phi r z, phi theta z. So phi r r means r momentum in r direction. As there is a no velocity in r direction, therefore we have no flux in r direction. So this term will be going to 0. Similarly, phi theta r, no velocity in r direction. So phi theta r is also going to 0. Same thing happens for phi z r. And when we are coming to phi r theta, theta velocity in r direction, the theta momentum in r direction. This means theta momentum in r direction. So we can see that here Vr is 0, V theta is 0, and tau r theta is equal to minus mu dVr by d theta. So it is also 0 as velocity Vr 0, V theta is 0, and dVr by d theta is also 0 as no velocity component in r direction. Therefore, we have all 3 component, net momentum is 0 for all 6 components. So we have only got these three these three components that maybe conclude some momentum. So phi zz, which we can write as p plus rho b z square plus tau zz, as velocity in z direction is, so this term is z, and pressure is also f, and tau zz, which we can write as minus mu dv z by dz, this one, as velocity in z direction is 0. No, as velocity is not varying in z direction, therefore this term is also equal to 0. So we have only remaining as p plus rho b z square, this term. We have only remaining this term, this one. So coming to the next term, phi r z, z momentum in r direction, which is right as rho br vz tau rz. Here we see that vz is exits bus, but br is not, as br is 0. So we have only tau rz, and tau rz is written as, you can see here, tau rz, yeah, tau rz, this one. It is, it will be some, have some value as velocity in, velocity, no, uh, yeah, it has some value as velocity in r direction have some value. It means that our velocity in r direction is varying. The velocity in z direction, this one, this component, only this component is exists, as we have velocity of in z direction is varying r direction. Therefore, we have some value of this, and phi theta z, which is written as rho p theta vz plus tau theta z. We have b theta equal to 0. Bz is not 0, but as b theta is 0, this term is going to be 0, and tau theta z is also 0, as there is a no velocity component in theta direction, and z velocity is not varying in theta direction. So this term is also going to be 0, which we can see here as that b theta db theta by dz is 0, no velocity component in z direction of theta. Same thing for this. So there is only phi zz and phi rz is concluding the flux. We have only all the 9 components. We have only 2 components that have some flux. So coming to the next part of it, that is cell momentum balance across small thickness dr of cylinder. We take a small thickness of dr of cylinder which have a length L and have a thickness dr. This one, thickness dr. Okay. So we write first of all what is the cell momentum balance. This is at rate of momentum in by convective transport, rate of momentum in by convective transport, and rate of momentum out by convective transport, and plus rate of momentum in molecular transport minus rate of momentum out by molecular transport, and this was the plus force of gravity acting on system equal to 0. This is the our cell momentum balance. So writing the balance for this small thickness of dr of cylinder. So we have a 5z component in at z equal to 0. At z equal to 0, we write a 5z component that is acting like this direction. So we have an area perpendicular to 5z. We have to take the area perpendicular to 5z minus 5z at z equal to L, and it means 5z is going from here and leave from there. At z equal to 0, at z equal to L, we have the area perpendicular to this as this one, this component, this circle, which is equal to 2 pi r into delta r, which is equal to 2 pi r into delta r. This term is equal to 2 pi r into delta r. And the next component is phi rz. Phi rz at r minus phi rz as r plus delta r plus 0, as there is no gravity component in horizontal direction. So we have to take it 0, equal to 0. So taking all the area and balancing all the thing by putting the values of phi zz, phi rz, we get this equation pz plus rho bz square into 2 pi r into delta r minus pz plus rho bz at z equal to L into 2 pi r into delta r plus 2 pi L into r tau rz at r minus 2 pi L r tau rz at r plus delta. Here we take the area, this area, here, this area, curved surface area, as the our rz momentum in from this side and out from there. So we have the area perpendicular to this as 2 pi r into L, 2 pi r into L, this one. We can clearly see that. And here 2 pi r plus delta r into L. As there is a variation in r direction, so we have to take a delta r small thickness. And now, as mentioned in the problem, pressure at both ends is same. We have given a problem that pressure at both the end of die is same. So therefore, P naught minus P naught is equal to 0, and rho b z square at z equal to L minus rho b z square at z equal to L also 0, as no variation of velocity of z component in z direction. Therefore, we remaining only with 2 pi L r tau rz at r equal to 0 minus 2 pi L r tau rz at r plus delta r. As Vz is not function of Fz, so equation reduced to by equation reduce, and we have to divide this equation by 2 pi L delta r. When we divide this, we get this equation. Limit r tends to 0, r tau rz at r minus r tau rz at r plus delta r upon delta r equal to 0, which is same as derivative of a function. So we write as minus d by dr r tau rz equal to 0. And now integrating this term, we get r tau rz equal to c1. We get r tau rz equal to c1. And again putting the value of tau rz, which is this minus mu dpz by dr. So putting this, we get minus r mu r into mu by dpz by dr equal to c1. Integrating again, we get dpz by dr minus c1 mu r. Integrating this, we get vz equal to minus c1 mu ln r plus c2. This is the equation we get after integrating 2 times the equation minus due to r tau rz by dr. Now applying boundary conditions at vz equal to 0. Vz is 0, no, vz is 0 at r equal to r2, as die is not moving. So if die is not moving, the fluid that is attached to that die is also remain to be zero, have a velocity zero. So applying this boundary condition, that is also called as no slip boundary condition, we get Vz equal to 0 at r equal to r2. Putting the values in this equation, we get 0 equal to minus c1 by mu ln r2 plus c2. And similarly at r equal to r1, b equal to bz. As our cylinder or wire is moving with velocity bz, and the fluid that is attached to that cylinder will also moving with a velocity bz. From there we can conclude that at r equal to r1, b equal to b1. Solving equation 13 and 14, we get minus c1 by mu equal to b upon ln r1 by r2. This thing. Similarly, putting this value, putting in now 13th equation, this equation, we get the some value of c2, that is equal to minus b upon ln r1 by r2 into ln r2. And when we put value of c1 and c2 in velocity equation, we get a proper equation of velocity, that is Vz equal to b upon ln r1 into ln r1 upon r2 into ln r by r2. So we get our velocity equation that they want from our question. And the next part is that they want the volumetric flow rate, Q, volumetric flow rate. So we know that volumetric flow rate is equal to the velocity into the perpendicular area. So we have the velocity Vz and perpendicular area for for cylindrical coordinate. For finding the average volumetric flow rate, we use this formula: integration of 0 to 2 pi integration from r1 to r2 vzr dr dθ. So taking common all the things that is constant 2 pi b upon ln r1 by r2 and integration of r1 by r2 r ln r dr. As we know that x ln x dx, integration of x ln x dx is equal to x square by 2 into ln x minus 1 by 2. So after solving this integration term and putting the values, you can see that they get a long term, this one. Here we can see that this term is cancelled with this term. So after equating all the term that will be cancelled, we get a equation of q equal to 2 pi v upon ln r1 by r2 into whole bracket r1 square minus r2 square upon 4 minus r1 square by 2 into ln r1 by r2. This is our volumetric flow rate for this question. Now the next part is that we have to find the force that required to pull the wire. So as we find the shear stress and we multiply if area, we get our force that we need to find. So for this, first of all, we have to find our shear stress that was act on our solid. Solid means on that is act on our wire. So shear stress that is acting on it at r equal to r1. At r equal to r1, you can see that this is our cylinder. Suppose this is our cylinder. There is a fluid. So at r equal to our r1, the fluid that act the stress on this wire, that will be our shear stress, which is responsible for required force for pulling the wire. So at r equal to r1, we first of all find our tau rz, which is equal to minus mu into b upon r1 into ln r1 by r2, and taking the perpendicular area, which is equal to 2 pi r1 into l. 2 pi r1 means that this one is a 2 pi r1 and the length is l. This will give the whole 2 pi r1 into l as a curved surface area. 2 pi r1 into l. So putting these values, we get our F wire is 2 pi L mu into V upon ln R1 by R2. And now coming to our last part of this question is flux profile and velocity profile, which is given as we have find the equation of velocity profile, which is Vz equal to B upon ln R1 by R2 into ln r by r2. Here r is varying. So we can see that velocity is varying logarithmically, and at r equal to r2 we have velocity 0, and at r equal to r1 we have velocity b. So we plot this and we get the velocity profile like this one. We get this velocity profile. And similarly for shear stress distribution, we have tau z equal to minus mu into b upon r ln r r1 by r2. Here we see that our shear stress is inversely proportional to r, so we get our shear stress profile like this. So this is the question. So we have concluded.
The person you are calling is currently busy. Please call again later.